first topic, argument. Argument is a list of given statement called premises, followed by the final statement be made called conclusion. It is consists of three techniques, which is the truth table, rules of inference, and laws of logic. However, in order to prove the validity of an argument, only truth table and rules of inference can be used. The first example of question in this topic is, from the argument, if the day is not rainy or not windy, then we will have a picnic and swimming. If we will have a picnic, then we will have sandwiches. We will not have sandwiches, therefore the day is rainy. We are asked to declare the primitive proposition and rewrite the argument using symbols. In this question, P will be used to represent the statement the day is rainy, Q as the day is windy, R as we will have a picnic, S as we will have swimming, and last but not least, T for the statement we will have sandwiches. Now, on the right-hand side, you will see the argument being written in its symbol form, where the first premise is in bracket, negation P or negation Q implies R and C in bracket, R implies T as the second premise, and negation T as the third premise. Last but not least, followed by P as the conclusion. Moving on to the second example, given the following argument, prove its validity by using truth table and rules of inference. From the truth table, it has been shown that all the premises logically implies to the conclusion R as it achieves tautology. Same goes by using the rules of inference. We are able to find the conclusion R through modus ponens, which is by taking into account all the premises. To conclude, both techniques did shows that the argument is valid. Now the third question, by using the laws of logic, show that P implies Q in bracket and P and Q in bracket implies P or Q is tautology. After simplifying the proposition by using equivalent identity, De Morgan's law, associative law, inverse law, idempotent law, and domination law, we did found out that the proposition logically equivalents to tautology. Therefore, it has been shown.
Next, I'm going to present the forward-backward method. The forward-backward method is a proof technique used in mathematics. It combines two types of reasoning: forward reasoning, which start from the given information, and backward reasoning, which start from what we want to prove. This method is very helpful when the question gives us more than one condition, because it allows us to connect the given information to the conclusion. For this method, we first identify the given information. We usually label them as A, the first given condition, B, the second given condition. In the forward step, we start from A and B and apply definition or algebraic step. In the backward step, we start from the statement to be proved and work backward to see what is needed. If both steps meet, then the statement is the first example. The question is, if n element to integer number and n is even, prove that n squared is even. The given information is A, n element to integer number, B, n equal to 2k, where k is element to integer number. Using the forward step, from B, we substitute n equal to 2k, so n square equal to all 2k square equal to 4k square. Using the backward step, we see that 4k square can be written as 2 in bracket 2k square, which is divisible by 2. Therefore, n square is if. The question is, if x more than 5 and x element to real number, prove that x squared more than 25. The given information is A, x element to real number, B, x more than 5. Using the backward step to prove x squared more than 25, we need x more than 5. Then using the forward step, since x more than 5, this directly implies that x more than 5. Hence, x squared more than 20. For the last example, the question is, if n is an integer and n is divisible by 4, prove that n is divisible by 2. The given information is A, n is an integer, B, n is divisible by 4, which means n can be written as 4k, where k is an integer. Using the forward step, we rewrite 4k as 2 times 2k. Using the backward step, any number that can be written as 2 times an integer is divisible by 2. Therefore, n is divisible by 2.
Hello everyone, today I'm going to explain the choose method. This method is used in set theory, especially when dealing with statements that involve universal quantifiers. The choose method is a technique for handling statements in the backward process that contain universal quantifiers. We use the choose method when B has universal quantifiers such as for all, for each, for every, or for any. So the statement is usually in this form. For every object with a certain property, something happens. What we do is we assume A, and then we choose a general object that has the given property. Finally, we conclude that something happens for that chosen. How we do it? First, we start with the given statement A implies B. Next, we check whether B contains a universal quantifier such as for all or for every. If B does not contain a universal quantifier, then we use another suitable method and then proceed to the ends. If yes, then we identify three things: the object, the certain property, and what we need to be shown. After that, we construct B1, then we construct A1 by choosing a general object with a given property. The object is general, not specific. Next, we construct B2, which is the statement that needs to be proven. We continue constructing A2, A3, and so on until we reach B2. Once B2 is reached, the proof is complete. This slide shows two examples of mathematical statements. First example, for every angle t, the square of sine of t plus the square of cosine of t is equal to 1. The object in this statement is the angle t. There is no specific condition, so this applies to all angles. What happens is that the square of sine t added to the square of cosine t always gives 1. So, this statement tells us that this relationship is true for every angle. Second example, for all real numbers y that are greater than 0, there exists a real number x such that 2 to the power of x is equal to y. The object here is the real number of y. The condition is that y must be greater than 0. What happens is that there exists a real number x where 2 to the power of x gives y. This means that every positive real number can be written as a power of 2. First, let us recall some basic definitions in set theory. The set S is a subset of a set T if and only if every element in S is also an element of T. Two sets S and T are equal if S is a subset of T and T is also a subset of S. Now, consider the following sets. Set S is a set of all real numbers x such that x squared minus 3x plus 2 is less than or equal to 0. Set T is the set of all real numbers x such that x is greater than or equal to 1 and less than or equal to 2. We want to show that S is a subset. To prove that S is a subset of T, we use the definition of a subset. This means that for every element x in S, the element x must also belong in T. Let us choose an arbitrary element A from set S. Since A belongs to S, it satisfies the inequality A squared minus 3a plus 2 is less than or equal to 0. We factor this expression as a minus 2 multiplied by a minus 1 is less than or equal to 0. A product is less than or equal to 0 when the value lies between its roots. Therefore, a must be greater than or equal to 1 and less than or equal to 2. This shows that a belongs to set T. So, every element on S is also an element of T, and the proof is complete. In conclusion, let S and T be the sets defined earlier. Take any element A from S. Because A squared minus 3a plus 2 is less than or equal to 0, we obtain that a minus 2 multiplied by a minus 1 is less than or equal to 0. This implies that A is between 1 and 2 inclusive. Therefore, A belongs to set T. Since this is true for every element in S, we conclude that S. Conclusion, let S and T be the sets defined earlier. Take any element A from S. Because A square minus 3A plus 2 is less than or equal to 0, we obtain that A minus 2 multiplied by A minus 1 is less than or equal to 0. This implies that A is between 1 and 2 inclusive. Therefore, A belongs to set T. Since this is true for every element in S, we conclude that S of T.
Hi, now I will explain for topic quantifiers. First, introduction. In logic and mathematics, quantifiers are in symbol or words used to describe how many elements in a group or set satisfy a particular statement or condition. They help us make statements that are precise, logical, and ambiguous instead of vague or general. Without quantifiers, statements like students are hardworking or numbers are positive can be unclear. Quantifiers clarify whether we mean all, some, or at least one. I will explain existential quantifiers. An existential quantifier means there exists or there is at least one. For example, there exists a natural number that is even and greater than 5. This statement is true because numbers like 6, 8, or 10 satisfy the condition. Key point. Only one valid example is needed to make the statement true. Next is the universal quantifier. A universal quantifier means for every or for all. For example, for every natural number, adding 0 gives the same number. This statement is true because it works for all natural numbers such as 1 plus 0 equals 1 and 2 plus 0 equals 2. Key point. If even one natural number did not satisfy this statement, it would be false. Next is translating word statements into logical expression involving quantifiers. Example 1. The statement is, every student in this class has a handful. First, we define the predicate. Let P of X mean X has a handful. The universal is all students in this class. Using a universal quantifier, the logical expression is for every X, P of X. If we use a larger universe, such as all people, we define let S of X mean S is a student in this class. So the full logical expression becomes for every X, if X is a student in this class, then X has a handful. Let's look at example 2. The statement is, some students in this class has visited England. Let P of X mean X has visited England. The universe is all students in this class. Using an existential quantifier, the logical expression is, there exists an X such that P of X. If the universe is all people, we define let S of X mean X is a student in this class. So, the complete logical expression is there exists an S such that X is a student in this class and X has visited England. Okay, now for negation of quantified statement. First, let us look at negation of quantified statement. Example, each student in this class has a handful. The statement uses a universal quantifier, which means for every student. The negation of this statement is, it is not true that each student in this class has a handful. This means there is at least one student in this class who does not have a handful. Key idea. The negation of for every becomes there exists. The negation of has become does not have. The last one is nested quantifiers. Next, we look at nested quantifiers. Nested quantifiers happen when one quantifier is inside another quantifier. Example, for all real numbers x and y, x plus y equals y plus x. Here, we use two universal quantifiers because the statement applies to all real numbers x and y. This statement is true because addition is commutative for all real numbers.
is mathematical induction? Mathematical induction is a proof method used to show a statement is true for all natural numbers, usually starting from n equals to 1 or sometimes n equals to 0. When do we use induction? We use mathematical induction when a statement involves n and we want to prove it is true for all value of n. Example, prove that a formula is true for n greater or equals to 1. Left-hand side and right-hand side method. The left-hand side and right-hand side method is applied in mathematical induction to prove a given statement where the main objective is to show that left-hand side equals to the right-hand side. In mathematical induction, the left-hand side and right-hand side method is used to prove the both sides of equation are equal. First, the base case is verified by substitute the smallest value of n, usually n equals to 1, into both sides of the equation. If the left-hand side and right-hand side give the same result, the base case is true. Next, the statement is assumed to be true for n. This means the left-hand side is equals to the right-hand side for some natural number n. For the step 3, which is the inductive step, the right-hand side is first written in terms of n plus 1. Then, starting from the left side, the expression is simplified step by step using the assumption of n. The simplification continues until the left-hand side becomes exactly the same as the right-hand side. Next, for n. Let us move to the example 1, which is for every integer n greater or equals to 1, where n summation I equals to 1. I cube equals to 1 over 6 times n plus 1 times 2n plus 1. We'll start with step 1, which is base case. Show that P1 is true. First, we check the base case, which is when n equals to 1. For the left-hand side, I got 1, and also for the right-hand side, I got 1. Since left-hand side equals to right-hand side, thus P1 is true. Step 2, which is inductive hypothesis. Assume Pn is true. Next, we assume the statement is true for some integer n. For step 3, show that Pn plus 1 is true. So the first, I start with substitute n plus 1 into the right-hand side equation first. After that, I simplify the expression and I got 1 over 6 times n plus 1 times n plus 2 times 2n plus 3. Then, we take a look for the left-hand side equation. I substitute n plus 1 into that equation and I got as shown. After that, I use the inductive hypothesis. I factor out n plus 1 and simplify it, and then I got the answer. Since left-hand side and right-hand side are the same, so Pn plus 1 is true. Therefore, by mathematical induction, the formula is true for all integer n greater or equal to the example 2, which is for the second equation, we prove the statement using mathematical induction. The statement is n summation k equals to 1, 3k to the power of 3 equals to 27 over 4, n to the power of 2 times 2 plus 1 to the power of 2. First, we check the base case when n equals to 1. The left side becomes 27 and the right-hand side also gives 27. So, P1 is true. Next, we assume the statement is true for n. So, n summation k equals to 1, 3k to the power of 3 equals to 27 over 4, n to the power of 2 times 2 plus n to the power of 2. For the step 3, which is show that Pn plus 1 is true, I usually start with substitute n plus 1 into the right-hand side expression first. After I simplify it, I got 27 over 4 times n plus 1 to the power of 2 times n plus 2 to the power of 2. After that, we take a look to the left-hand side expression. I already substitute n plus 1 into it, as you can see right here. After that, I factorize out 1 over 4 from the bracket and it's gonna form a quadratic expression. After that, I factorize the quadratic expression, then I multiply 1 over 4 with 27. After that, we get 27 over 4 times n plus 1 to the power of 2 times n plus 2 to the power of 2, which are the same as right-hand side expression above. So that means left-hand side equals to the right-hand side. Thus, Pn plus 1 example, which is last example, show that for all n greater or equals to 1, where n summation I equals to 1 times 4i minus 1 equals to n times 2n plus 1. So as usual, we start by show that P1 is true. So for this equation, as you can see right here, I already got, which is left-hand side is 3 and right-hand side is also 3, which means P1 is true. So we move to the second step, assume that Pn is true. So the equation is going to be n summation I equals to 1 in the bracket 4i minus 1 equals to n times 2n plus 1. So we move to the second step as usual, assume that Pn is true. So Pn equals to n summation I equals to 1 times 4i minus 1 equals to n times 2n plus 1. For the last step, which is show that Pn plus 1 is true. As you can see right here, I already substitute the n plus 1 into the right hand side expression and get n plus 1 times 2n plus 3. After that, we move to the left hand side expression. I already substitute it right here, and I also use inductive hypothesis. After factorizing it and simplifying it, I got the answer as same as the right hand side expression. That's mean Pn plus 1 is true.